This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Standard chemistry treats a molecule as a static arrangement of dots and lines, a clean, predictable graph of nodes and edges floating in an empty void. This model assumes that reactivity is an external event that occurs only after a structure is finished, completely ignoring the physical context where that structure exists. This reductionist view fails when we look at the messy reality of biological chemistry, the complex supramolecular assemblies, and the shifting interfaces at the edge of a cell membrane. In these systems, the surrounding solvent and the weak interactions between molecules override the static atomic bonds. The environment effectively dictates the chemical reality. Focusing on isolated structural graphs hides the actual mechanisms that allow persistent biological organization to emerge from raw chemistry. The molecular chemical fabric, or MCF, replaces the isolated graph with a continuous operational state. In a fabric, the primary structure is mathematically integrated with the weak interactions, the environment, and the accessible reaction pathways. This framework tracks how isolated reactions move up a ladder of complexity toward the threshold of a living system. That endpoint is the Life Sciences Fabric, the point where chemistry functions as a self-regulating biological system. The origin of life is a programmatic, computable transition between these two fabrics that can be formally mapped and predicted. Mapping this transition begins at the absolute foundational level, the individual chemical bond. Through pre-topological preselection, a bond's internal architecture structurally privileges certain future reactions before any external catalyst is even introduced. This schematic reveals the reactive transfer image of a bond. We measure cleavage bias, the likelihood of a rupture, against persistence bias, which provides structural stability. Persistence establishes the molecular skeleton, while cleavage creates specific corridors for dynamic transformation. Environmental factors like solvent density or interface boundaries can shift these innate biases, turning a stable bond into a reactive gate for the rest of the network. Primary molecular structure acts as a pre-filter, mathematically narrowing down the possible chemical pathways before a single interaction begins. Expanding the scope from individual bonds to regional networks allows us to see how these pre-selected pathways interact within a specific environment. A single catalytic loop is too fragile to generate lifelike chemistry. These loops must couple together to survive. Every chemical region is defined by retention-escape competition. Some pathways bleed outward into dissipation, while retentive corridors form closed self-reinforcing loops. These retentive corridors must mutually reinforce one another, thickening internal circulation until the dissipative escape routes are effectively suppressed. This creates a strong organizational basin, the first genuine chemical habitat capable of sustaining itself. Without an organizational basin, a chemical system lacks the structural foundation to act as a proto-metabolic network. Organizational basins cannot scale up their complexity indefinitely without hitting a rigid regulatory limit. The bioelectric transition gate is the formal boundary condition that separates chemistry from systems biology. Passing this gate requires electrochemical readiness, distinct spatial protogradients, and physical compartmentalization. Attempting to scale a network without these specific gradient and compartment structures results in immediate system instability and decay. This electrochemical threshold represents a mandatory architectural upgrade that chemistry must clear to become biological life. Crossing the gate shifts the system into the multi-layered architecture of the life sciences fabric. This is the canonical decomposition of a living system. It defines life as a set of 5 self-regulating dynamical variables. The physical structure of the system generates a regulating bioelectric field. This field informs continuous control mechanisms, which execute structure updates to maintain the system's persistence against decay. Metabolism provides the necessary energy flow, while memory encodes historical states to allow for long-term adaptation. Life exists only when these 5 continuous, feedback-driven regulatory loops successfully couple together to outcompete physical entropy. These architectural laws operate as an executable computational system. The MCF autonomous agent layer uses algorithmic loops to evaluate, extract, and rank chemical systems within this framework. In the Process Graph Studio, raw chemical data is normalized into a fabric topology, revealing the recurrent regions that sustain the system. The Threshold Explorer then scans these graphs to find organizational basins and rank their viability for biological transition. Using the lens engine, the system can calculate the minimal structural patches needed to artificially drive a failing chemical network over the bioelectric gate. Machine logic turns the complex origin of life and synthetic biological design into a deterministic, computable extraction problem. Computational outputs from this engine translate directly into laboratory interventions. Theoretical LSF variables map to physical measurements, allowing researchers to track metabolic flux and spatial voltage gradients in real time. This creates an intervention feedback loop where software predictions guide precise chemical and electrical perturbations to stabilize or modify a physical structure. These advanced systems enables targeted regenerative tissue repair and the highly reliable engineering of completely novel synthetic biological units. The framework spans from the localized reactive bias of a single bond to the autonomous execution of biological control. By formalizing chemistry and biology into a unified, computable fabric, we gain the ability to engineer the architecture of life directly.